Hello, lazy chemists, and welcome to today's lecture where we are going to be talking about enthalpy. Okay? And enthalpy is a topic we've covered it before if you've taken a sophomore chemistry class or even a freshman chemistry class before. But it's good to have a nice little refresher here and to remind you of what a couple of these things look at. Here, you're going to be able to see some of the main topics. And I'm also going to go ahead and show you some shortcut ideas for us to go ahead and think about. So first what we're going to do is we're going to go ahead and define enthalpy. Okay, so this is our first dot that we're heading to. What is enthalpy? Okay. And enthalpy is going to be essentially a measurement that allows us to calculate the internal heat or the energy that's within a system. And we're going to go ahead and define some of these things a little bit more closely here. And I'm going to want you to record all these down. But first we're going to go ahead and define enthalpy as what it is, the internal energy of a system. So go ahead and write this definition down. And now we'll go ahead and say, okay, so what does that mean? Let's talk about a system. So what is a system? And in this case, a system is going to be the reaction vessel or the device or whatever is being measured. So whatever thing that we're interested in, whatever change that we are trying to do is going to be our system. Okay? This is going to be followed by our surroundings, and that's going to be everything that is not in our system, okay? So we have what's in the system, and then we have the surroundings that are outside of the system. And then we have the universe, and the universe is both a combination of the system and the surroundings, okay? So that means that enthalpy is going to be our measurement for what we're doing in particular to our system, okay? And one of the things that we're going to talk about is, energy coming in from the surroundings or leaving from the surroundings, okay? So that's going to be a topic that we're going to be going over here. Now, one thing to keep in mind is that the enthalpy or the total energy of the universe is going to end up staying at 0, okay? So energy is not created or destroyed, which means that we're going to either, if we're losing some energy from the system, that means it has to go to surroundings. And if we're gaining energy into the system, that means it has to come in from surroundings. So those are some terms that you're going to have to be able to think about and use kind of together. So they're always going to be paired together. Okay? And this is going to kind of lead us into the chemistry discussion of the first law of thermodynamics. And those of you that are taking physics, this is going to be something that's really kind of basic for a review here, because we're going to understand it here in the chemistry way. And the basic law states that any changes in the internal energy of a system, which in this case, this is going to be delta U, so any changes in energy, are going to be transformed to Q, which is going to be heat, and work, okay? So these are going to be the things. And work is usually defined as pressure volume work, okay? So I want you to go ahead and think about what we're thinking about in terms of work is going to be we light a chemical reaction on fire and it expands and it drives a piston. That's an example of work. Like that driving, that moving of that piston, that expansion of gas in the piston of a car is an example of work that's being done. It's pressure volume work that's being done. But the main thing that we're concerned with, and we're going to be, manipulating here in chemistry, is that the total energy of a closed system is going to remain constant, okay? And for the most part, we're going to try and consider most of our systems closed. We're going to use things that are called calorimeters, and those help to create a more closed system. And even though in our examples they're not going to be perfectly closed systems, for the most part, any inflowing of energy from the surroundings is going to be negligible. Or outflowing, for that matter, either. Okay. Therefore, if we can make it so that there's no pressure volume work, that means that we can go ahead and determine energy gained or lost in a system based off of heat. So if we're able to reduce this PV work to 0, then usually we'll be able to determine the energy change of a system just based off of heat. And that's what we're going to be manipulating here in most of our chemistry problems, is this Q. We're going to say, okay, well, W, let's get that to 0, and let's manipulate this Q right here. Okay. And remember that Q represents heat. This is another form that we can go ahead and work with. And usually at this level of chemistry, we start worrying about the lazy way, which is the tabulated way. Okay, so we have a lot of different enthalpies ready to go. We have a lot of them calculated. We've already put them in tables. And in fact, a lot of them can be, searched up on a regular data table. I actually have a data table here in my office that's in qualitative analysis and electrolytic solutions, and that's by Edward J. King. And that has a whole large data table that has a whole bunch of enthalpy changes in it. And also, no judgment. I know I'm a nerd. Okay, I know that I have the nerdiest books here. And the simplified formula that we're going to use for this, for these types that use tabulated values, is going to be that our change of enthalpy, okay? Because throughout this unit, we're going to be changing enthalpy. So we're going to be doing chemical reactions, and those chemical reactions are going to involve a change of energy. Our change of internal energy of a reaction is going to equal the change of our final products, or the internal energy of our final products, minus the internal energy of our initial products. Okay? So, a change of internal energy of our final products minus the initial, or the internal energy of our initial products. Okay? So this is final, this is initial. And that'll give us our total change. And this is more than often what we're looking for. Sometimes you'll see some problems where you're given the total change and you'll have to find like the initial state or the final state. But in general, for most applications, you're going to look for this total. Okay? And this is going to bring us into the last little mini topic here, which is going to be exothermic or endothermic. And exothermic is going to be any reaction where energy is lost, where the internal energy is lost to the surroundings. Okay. And that's going to mean that the energy that was originally within the bonds, within the molecules, that was being pent up, that potential energy, is lost as kinetic energy. And it's lost usually as heat. So in general, if something feels warm, that's an exothermic reaction, and that reaction, or the chemicals that are participating in that action, have lost energy somehow. Whereas an endothermic reaction, that's going to be any reaction in which the system takes in energy from the surroundings. Okay, and in general, that's going to feel cold to you, because what's actually happening is that it's taking some of that kinetic energy that's within the atoms that are in your skin, in your cells, and it's absorbing some of that energy, which makes it feel cold to you. And that's what, cold is. That's the loss of energy to an outside source. All right. And we're going to go ahead and take a look here at a graph. Can we go in further? And this is an example of a typical energy diagram. And all of these things we're going to get familiar with, so we might as well copy out the diagram as it is. I did take this one from Khan because it is nice and colorful. And this is an example first of a exothermic diagram. And here you see that our reactants have a high potential energy. Okay, so that's the energy that's stored within the molecules. We activate and get them to a transition state. And I'm going to show you how to go ahead and figure that out. This is usually some intermediary state where we've given them just a little bit more energy so that they can get going. If you think about, the fact that if you're going to light let's say a grill or a stovetop, that you have to add a little bit of heat through flame in order to get that reaction going. Okay. And then sometimes that reaction will keep going because you keep adding the same amount of initial heat. And then this transition state is like the intermediary state. You might get intermediary molecules. You might get some temporary bonding that's going in here. And we're going to be talking about that in this section, but we're also going to go ahead and talk about this a lot in organic chemistry as well. This right here is our activation energy. It's the energy required to get it going. And you see that our products here are lower in potential energy. Okay. And here we have a loss of delta H. Since this is a loss of energy, a loss of potential or internal energy, this should be a negative delta H. Okay, and that's what exothermic is. The next one's endothermic. Endothermic has a lower potential energy to start with. Then we have activation energy here, bringing it to a high transition state. And then our products will end up being at a higher state than they were before. Okay, so it takes a lot of energy to get these going, but once it does, you're usually pretty good to go. Okay. And here the delta H would end up being positive because we end up having an increase in energy. Okay. And typically we think about, endothermic processes as anything that absorbs in energy and then creates a product that has more stored energy. And the prototypical example that we'll use is photosynthesis, where it's actually taking in light, and it's using that light to form like an electron chain. In order to create sugars and glucose that have a high amount of energy. Whereas carbon dioxide, we typically think of that as having a low amount of potential energy. Okay. That's going to be it for this lecture here on enthalpy. This is really just a basic get to know your main topic with a couple of definitions. I'm going to let you know that the graphs in particular are something you're definitely going to want to know. I'm going to expect that you're going to be able to see a reaction and be able to determine based off of what type of reaction it is, whether it's going to be an exothermic or an endothermic reaction, and then label where all the reactants would go, where your products would go, whether the delta H is positive or negative, and different things like that. At this point, we're going to go ahead and close this lecture out and give you time to work on whatever materials you need to work on. As a parting word, I can go ahead and tell you that this section, including enthalpy and in general thermodynamics, is one of my favorites because this is the section of essentially seeing how much energy we can produce And usually producing a greater amount of energy in a small amount of time is what makes those explosions that really make or exemplify some of the joys of chemistry. But at this moment, I'm going to go ahead and leave you guys off. And remember, stay lazy.